Welcome back. So I'm going to give you an introduction into machine learning, and the objectives of this talk is that you, in the end, you can make sense of terms and concepts that are often heard, that you get an overview of some methods and their strategies, and that you can then also apply maybe 2 up to 4 machine learning techniques, and that you will also learn and be critical. Machine learning does not solve all of your problems. And a small example here, I once saw on a poster on a conference, someone computed all the possible models that were by then in the caret package, and did like model averaging of like more than 70 models he trained. And I want you to be able to judge in the end, this is a sensible thing to do or not. And of course, to be able to reason why. So that's the content of the lecture, terms and concepts. So then we will take a step back. What do we actually need? Then I will give an overview of the machine learning methods. Is it then taking the right microphone? It's good? Okay. So I'll also think something about overfitting. What is this exactly? And then we have a look at the different methods, the Lasso, support vector machines, and some ensemble learners. So first, in terms of concepts, I mean, machine learning, it's a discipline, some sort of at the intersection of computer science and statistics and math. And depending where the people are coming from, they use also a bit of different vocabulary. And from my point of view, I actually prefer the term of statistical learning, or like computational statistics, to stress more that these are all methods that have like a well-founded background in statistics and math, and it's not just plain and like it's not just plain algorithms. It's all well-founded if one takes the time to have a closer look. So we divide the fields of unsupervised learning and supervised learning. And unsupervised learning is you basically just have covariates. You don't have a response, and you try to find the structure that you have in your data without actually knowing what your output will be. So it has like a more exploratory character, and it's, for example, used to cluster the pixels of satellite images, and then for these clusters, in a second step, you can try to assign the actual values. Some sort of operating blind and really without like targeting a response. Supervised learning, we always have like a clear response value, and we have covariates, explanatory variables that are trying to explain our response. So, for example, a linear regression would be a supervised learning, a random forest, and that's what we usually do if we do mapping of a specific response. For example, in my work, I want to know the clay content, so this is clearly like a supervised learning task. We can have classes, we can have continuous responses, so this doesn't matter. I really advise you to do further learning. You will not walk out of here knowing everything. And I warmly recommend you the book of Gares. This is really a short introduction, very well explained, and it also has like R code examples. If you want to go further, I recommend the book of Hasty and his colleagues. but this is the book without R examples. It's really explaining the background. And especially if you do a PhD and apply such methods, I really recommend you at least to read the chapter of that method you use. Even though you might do not understand everything, but please get some background knowledge. Then, moreover, there is the book of Kuhn. That's the author of this meta package caret that already Hannah showed, and I think also others. I find this book a bit, I don't know, too much text. It could be clearer, shorter, and easier explained. But also feel free to consult that. And what's always a good thing is these Cran task views. I don't know if you're aware of those. Thorsten Hothorn is maintaining the one on machine learning. And this is basically giving an overview of all the R packages there are to do anything related to machine learning. So if you know of a method, but you don't know if it's how to do it in R, then that's where you can have a look. So first, a step back. I mean, my situation during my PhD was I have like 300 to more than 1,000 locations where I have measurements. I have like 2 to 4 different depth intervals, so really many responses in 3 study areas. And on the other hand, I have like 300 to 500 possible covariates out of terrain analysis, out of hyperspectral imagery. And in the end, I really have many models that need fitting. And but what I needed is basically, I know there are non-linear relationships, so I cannot just go with a linear model. Further, this is spatial data, so I also want them, these models to consider the spatial autocorrelation. I have not just like continuous regression data, I also have classes. I even had ordered classes. So, and I have really many covariates, and they are partly correlated. So I need a method that can handle that. And because I have so many models, I'd like to automatically fit the model without too much user interaction. And a further point we were looking at, too complex models, they usually lack a bit of acceptance. If I show a very complex model to a soil surveyor, he wants to know what's the relationship. And if I can't tell the soil surveyor, they usually disappointed and think, oh, it might be not a good model because we cannot understand it. So a model should be sparse, possibly. So not contain too many complex relationships that are not necessary. And we want to accurately quantify the accuracy. So, and give prediction uncertainty. So we want to have prediction intervals. So that's the list, what an ideal method should fulfill, for at least for my work. And for your work, you should always also take a step back and not just, oh, I use a random forest. Maybe just think what's actually, what's my aim, what do I need, and what's the requirements I need this method need to fulfill. So what possible strategies and machine learning methods do we have? I tried to structure all these possible methods a bit. There are different ways how you can structure it, but it's like one way to group them as some sort of a bit in the families. So we have, like, for example, classical regression linear models, but also non-linear models that these models, they always assume a certain distribution for your errors. This is also like if you have like additive models, they also have a certain assumption of the distribution of the part that is not explained in your model. And I would also put the geostatistics here because the like a kriging approach, external drift kriging or regression kriging, how it's often called, it takes a linear model and then it further considers the spatial correlation in the data. Then there are methods that are used for dimension reduction, like principal component analysis, factor analysis. They do some decorrelation of your data and transformation of your data to reduce the dimensions. We have a whole group of shrinkage and regularization. We will have a look at that later. And the Bayesian methods, that's where I would put inline. That goes here. Then, of course, we have like tree-based methods, decision trees, neural networks. I think you have like introduction on that on Monday with the deep learning. Support vector machines, the kernel methods. I will show an example of that as well. And then we have ensemble methods that are actually like putting several models together, several models of the same type or also of different types. That's where I put random forest, because it's combining several decision trees. So the upper row, I consider like linear or parametric more or less, and the models down here, you can consider like a quite high complexity, and this means also quite flexible to adapt to your data, but also flexible to overfit, maybe. So now on overfitting. This is a figure I took from the book of Hasty, and you have like the prediction error, and then you have the model complexity from low to high, and you have a training sample, that's where you fit the model, and a test sample. And you have, if the complexity of your model is increasing, then of course, the better you fit your training data. Your model starts to over-adapt to your training data, but then it has difficulties to predict data points that the model that has not seen. So there is, at some point, there is an optimum where the test sample can be predicted well, but if the complexity increases, the test sample will not be predicted well anymore, because it's just the model is over-adapting to your training data, and it's not generally applicable anymore. It's not learning general relationships, but just relationships that are possible artifacts of measurements in your training data. And this means, like, if we are to this side, we are usually like having low complexity models usually tend to have a high bias. They tend to be systematically off, but low variance, and high complexity models have high variance and usually lower bias. I explain it just on the next slide. So here, for example, on this panel, we have a linear model. This is quite a complex data pattern, and with this linear model, you can, of course, not follow the pattern very closely. So it's some sort of systematically not fitting well the data, but the line, depending on how you estimate this line, it's quite stable. And on the other hand, you have like here a one nearest neighbor approach. This is a clustering approach, and this is like having a low bias because it's fitting your data very well. But if you just change one data point, your model will change quite a lot. This means your model will jump around, and this means it has a high variance. And basically, that's also what we already talked this morning. You have here the expectation of your squared model error. Basically, this is the observation, and f a function of x. This is your estimated model. Y minus your model gives your squared gives your model error, And this can be decomposed in a part, the bias and the variance, and of course the error, that is the rest that is not explained by your model. So if usually like procedures like this that are less flexible introduce a higher bias, and procedures like this introduce a higher variance in your final model error, mean squared error, for example. So this brings me already to the methods. Are there questions so far? So then we have a look on the Lasso. Okay. The Lasso is basically it's at the basis of linear regression. Oops, excuse me. And maybe you are aware of in linear regression there is in R is this step function where you can do stepwise forward and stepwise backward model selection. This means you take in a covariate or you leave it out, but it's always, it's either in or it's out, and the coefficient is fully fitted. That is, it's a binary decision if you use a covariate or not. And the idea behind this shrinkage models is that you can use a covariate, but you don't have to use them for 100%. You can, but their coefficients are shrunken. This means they are pushed to be a bit smaller. This means you can also like use a covariate just for 30%. If it's not so important, it's the coefficient is going to be smaller than in a normal linear model. This means the function to estimate such a model is downweighting the coefficients. And there are basically different approaches. One is also called ridge regression or elastic net, how you can actually then estimate the coefficients of such a linear model. But I now show the Lasso, because it's also quite easily to be implemented in R. This Lasso coefficients of your Lasso linear model, they are basically computed as such. This part is the normal ordinary least squares, and this part comes in just specifically just for the Lasso. So basically you have again your observation minus the beta 0, that's the intercept, minus then the sum of all your covariates multiplied by the coefficients that are attached to these covariates, and squared because it's ordinary least squared, of course. And then here you basically add the absolute value of your coefficients, and those are supposed to get small, and with this lambda parameter you can control how much you want to shrink, how strong this penalty should be on the coefficients, and how much they should be forced to get small. So this Lasso is then some sort of like with this lambda parameter doing a continuous subset selection or continuous covariate selection. And this, the value of this lambda is then to be found with a cross-validation. So here you can see, for example, how this behaves. This shrinkage factor here in this graph is called S. As we increase it, so this means there is the penalty is loosened. The coefficients, these are the single covariates, are then like getting higher and higher, or like larger and larger. There is just one lambda, because here you calculate the sum of the absolute value of the coefficients. So if this shrinkage can even be so strong that one covariate becomes a zero coefficient, and this means it's getting removed from the model, and therefore we also have like a model selection tool that we can remove covariates. Here you can see a graph of this cross-validation for the log lambda and the cross-validation error, and here above you basically have the number of covariates in your model. Here for this example I had like more than 400 covariates, and I found the minimal error somewhere around 70 covariates. And if you really want to have a very small model, you still use +1 standard error of your cross-validation errors. So you can even have like the model was then around 30 covariates in the end. As a tool, the pros and cons of Lasso, it's very fast. The algorithm implemented behind it is operating very fast, even on large data sets. It selects covariates as it puts coefficients to 0. If you have collinear data, this is if you fit a normal ordinary regression and you have two covariates that are correlated, they both get might get a very large coefficient. One has a positive coefficient and one a negative coefficient, and so you get these very unstable model fits. This is with this shrinkage, this is not possible here in Lasso, so you can even add correlated covariates without a problem. You don't have to pre-select them beforehand. And it's easy interpretation. Interpretation remains as with a normal linear model. And the linear regression is even possible if you have, let's say, 50 data points and you want to fit 100 covariates. The algorithm can handle that. In an ordinary least squares regression, this is not, a model fit is not possible in this setting. But the disadvantages of this approach, you remain completely in a linear framework. This means you also need, if the errors follow a Gaussian distribution, if they don't, you are on the wrong model assumptions, and the model fit might not get optimal. This means you also have to take care of transformation of your response. And I mean, it remains a linear framework. You don't, if there are interactions, they are not automatically covered. You can add them manually, but if you don't know about them, it's usually a bit difficult to know where are the interactions in your data. And from my point of view, it's sometimes it resulted a bit in weird model fits. I don't know, but I mean, this was about my data, but I couldn't find what was actually wrong with my data when I got the. So one has to take a closer look if the fit was really working properly. And I think it's rather underfitting. So it remains a linear model. It's usually removing a lot of covariates, and so maybe it does not really find all the complexity in your relationships in your data. And the standard errors are not defined. Prediction uncertainty can only be gained by a bootstrap approach. You will see this this afternoon. And it's not a spatial method. It's you have to introduce coordinates as covariates or rotated coordinates. It's not like a kriging approach using the spatial dependencies in your data. So, are there questions so far on the Lasso? I've already heard someone try to use it on the competition data.
So it's very fast.
It's very fast, yeah. I've not tried with thousands, but this coordinate descent algorithm that is behind is very fast. It's very efficiently implemented, and it's not it's not rising by the number of coordinate data points, but rather by the number of covariates. That is usually not as big.
And then we should like for linear relationship, covariate.
It's possible, but you could, if you know about that relationship, you could start to do transformations of also of your covariates.
But you have to know which one you have to do.
Exactly, exactly. It's not automatically taking care about it.
And the last one was what if you have same conditions where you extrapolate, so you have bias, extrapolation. How does the last one
I mean, it's a linear model in the end, and it extrapolates beyond its boundaries. That's it's in the end you have a linear model. It's just differently how you fit the coefficients. Anatol? The question was if Lasso is generally underfitting, if it would be meaningful not to use this one standard error rule. I'd say yes, but this means you need to know if it's underfitting. This means you need to have like an external test set where you can actually evaluate that. And for me, I usually used Lasso as some sort of a covariate selection tool. And then I could, with these 30 covariates, I could continue in, for example, a kriging step. So to use it as like the final model, I'd say it might not be so promising, but it's a tool that can be used in some workflow in a chain at some point where you need to select covariates for a linear model that cannot be fitted otherwise. The question was if the dimensions match up, and you mean like the different value ranges of your covariates that can be really like one covariate really large values and others very small ones. The data is, if I'm not mistaken, the data is normalized internally. If the data is normalized, then not, because then they are on the same level. But of course, the problem remains as in an ordinary least squares, that you have like large coefficients, maybe for data that has typically also large values in its original data set. Any other questions? I'll check here. There is a question, how is bias defined statistically? Bias is usually calculated, but I think there is no general definition that you could say it's that's it. It's usually calculated as the sum of the mean error. So basically y minus your estimate and then summed up. But there is also an absolute mean error, like the robust version of bias that could be computed. there are no more questions, we continue to the support vector machines. This is a method that came from the classification side. And it is basically in a classification setting. The support vector machines are basically trying to split your data into two parts if you have a classification of like yes or no. And this is done by a line, or if you go into like, if you have more than one covariate or like 2 or 3 covariates, it's then advancing into a hyperspace. So you fit then a hyperplane, and this plane is then defined not by all of your data, but it searches for the closest by data points that are then building up this hyperplane. And these are then the so-called support vectors. And this means it's this plane is fitted along, really along where the separation of your data is. And if you have like outliers that are a bit far off of your normal distribution, they are not considered in the data fitting. And now, of course, all of the data is not actually, you cannot split all of the data of your data sets exactly with one line. So there are parameters that allow for points being on the wrong side. So these are then called soft margins, and a support vector machine classifier is then like, you can then define with this tuning parameter C how many of the points are allowed within this margin. And this means your support vectors are further away from your hyperplane, and these points that are within the margins, they are allowed to be wrongly classified. And this is basically describing how flexible your tool is allowed to be in the end. So larger values of C, as in the top panel, will then result like in a higher tolerance for points being on the wrong side, and lower values of C will then result in a lower tolerance of being within this margin within the wrong side of the hyperplane. And this is like one of the tuning parameters we have to choose. And the other one is, of course, here you see like we have a linear, we have a plane, and our relationships might not be linear, so we can use radial kernels instead of a linear separator. So, for example, here you have like this data, it's actually clustering quite well, but with a linear classifier, we will never be able to split it properly. So we need something that looks like this. And the soft margin also applies for these radial kernels that are then used. So we basically have this two tuning parameters. One is how many points are allowed to be on the wrong side, and how non-linear is our model supposed to get, and how flexible is our kernel allowed to be. And these two, we have basically these two tuning parameters. We are basically defined with cross-validation again. For the support vector machines, my experience so far, I found them quite fast. It's a method that is robust to outliers because it's really only considering the values that are close to these separating planes or separating functions. Of course, it handles nonlinear relationship, and the linearity or the non-linearity is a tuning parameter that you can choose. From the literature, as far as when I saw this, like studies comparing different methods, this was usually a method performing quite well, and it's quite easy to apply. So I included it also in the tutorial later. But if you have 100 covariates, you will not be able to select any covariates, they will all remain in the model. And interpretation is, from my point of view, quite difficult. You don't have a thing like covariate importance. And of course, you can plot partial dependence plots. We will see this afternoon. But if you have 100 of these plots, how can you, what's the interpretation then in the end? And again, standard errors are not defined. Prediction uncertainty is again only with a bootstrap approach. And again, the same problem as with Lasso, it's not a spatial approach. We have to include the spatial locations in with some workaround. Are there questions so far? So we proceed to the ensemble learners, where the first is random forest. First, ensemble learners, it's basically you combine different learning methods. And this is usually very meaningful if you have a procedure that has a low bias. So on average, it's correct, but it's usually, it has a high variance, but it's flipping around a lot. If you remember, like this clustering, with the k-means clustering, just if you change one point, the model will change. So but in the end, if you take the average of many such flipping around models, it has shown that, that they give good predictions. So there are different strategies. One is called backing bootstrap aggregation. There you basically do a resampling of the data with a replacement and fit your model to the resampled data. And resampling is just like taking at random out of your data, and data points can be selected twice, 3 times, and so on for your fitting data set. And you do this maybe 500 times, maybe 100 times, until you have like a stable model fits. And the prediction is then of such a procedure is usually like the average of your 500 models. Then another approach is gradient boosting. This is a strategy that is some sort of stepwise forward strategy. I will show that later on. With the bagging, you basically do not change your distribution because you have a random sample of your original data. With the gradient boosting, you always fit on your residuals. So this means every model has like a new underlying distribution in the original data. And the model averaging is basically you fit a bunch of different models and you take a strategy to combine the predictions of these. So random forest is an ensemble learner that has the classification and regression trees as its basis. And they are based on recursive binary splitting. So you always split your data into 2 sets. And for every split, you check all your covariates and you find your optimal covariate for every split. Or for every split, you restart this procedure. And you basically grow a large number of these trees. And now it's important that these trees are not similar. So the more dissimilar they are, the better you expect to get a good prediction. So random forest takes like 2 strategies to get trees that are not similar. So one is this resampling, this bagging bootstrap aggregation procedure. You basically take a random sample of your data and fit to this data. And this resampling is basically done if you have 100 data points, you take at random also 100 data points out of those. And then it's not using all of the covariates at each split. This is this mtry parameter. So at each split, it's just trying like 1/3 of the covariates to find the best covariate for this exact split. And the prediction in the end is the average of all trees. And for the continuous responses, and of course for classification, is the majority vote. So how is this algorithm working? You basically first you resample this data set with a replacement. Then you take a random sample of your covariates. And how many you randomly sample here, this is this mtry tuning parameter. You test all the selected covariates for this split to split your data into 2 portions. And this is, in the most implementations, is done by minimizing the squared error or the wrongly classified. There is also some work that there could be other criteria to find the optimal split, but I'm not sure if this is already implemented. And then you choose basically the covariate that has the lowest error, and you continue with splitting until you have a minimal set of data points that is defined in this node size. It's usually 5. If you have like 5 data points remaining, you stop splitting. And then you keep repeating this for all trees. And as you can see here, your data is then getting sorted, hopefully, regarding your response into groups that have similar properties. So the first resampling and second resampling, the data looks a bit different. And of course, if you have like different covariates that are being tried at each splitting, the tree will look different. So the main tuning parameters is this mtry, how many covariates you test, the number of trees, but this is usually not sensitive as long as you grow a large number of trees. If you grow of 500 upwards, it's usually not a sensitive tuning parameter. And the node size is usually also not sensitive. If you use the default there, that's usually fine. So now, most of you likely heard of this out-of-bag error. Now, what's that exactly? According to Hayes, this is for each observation set, you construct its random forest predictor by averaging only those trees corresponding to the bootstrap samples which did not appear in set. So basically you have this, you sample with replacement, and usually with this procedure, about 30% are not taken into your actual sample for this one tree. And for this 30%, you then you fit the tree, where these roughly 30% are left out. And then this gives you directly a validation sample for this single tree. This means you then, for this 70% that are taken into the sample, you fit the tree, and you compute predictions for the ones that have not been used for this tree. This is basically, it's like a cross-validation. You have data that has been left out for this single tree, and of course you have 500 trees, then this is a bootstrap validation approach. And you have like immediately like a cross-validation error independently. But of course, if you remember also the talk of Hannah, it's if you have like spatial dependencies in this data, or your data is not from a statistical design, you might still have not a biased prediction of your final R-square, also even with this out-of-bag error. So random forest is, again, if you do not endless tuning, it's quite fast. it really models interactions. Since it's a tree-based method, it can handle really very complex nonlinear relationships. Many studies show that it's really a good predictor, and it's in many studies outperforming other predictors. It has a covariate importance, and with this we can continue with interpretation. We can continue with model selection, for example, and with this quantile regression forest for regression problems, we also directly have prediction uncertainty and can construct prediction intervals. But if we just add in all of our covariates, still it can be difficult for interpretation because, yeah, but that's a general problem. And just like blindly applying a random forest without any proper validation will not give you the holy grail. And again, it's not a spatial method. It does not include the coordinates in any systematic way. Any questions so far? I mean, since we have the prediction of a random forest is the average of the values where your data point ends up. So if you do a prediction, you basically follow down the tree and then you take the mean. So it can never go beyond that mean. This means random forest or any other tree-based method that predicts like that cannot extrapolate. It will just like remain on the mean of the single leaf. Yeah, exactly. And with support vector machines, I'm not too sure about the extrapolation behavior. I'd say it's not like as strict, not extrapolating in the feature space as a random forest, but it's not as strong as a linear model that clearly follows the line. But I mean, that's again the topic of Hannah's talk, like extrapolating in a feature space where you do not have any calibration data. Should be done with care with any method, even if it's like random forest that doesn't even allow it or doesn't allow it. It just uses the last value it has seen. Doesn't mean that this is correct.
The data set, the two biggest is the overfitting and the extrapolation.
Biased samples.
Biased samples.
Yes.
Extrapolation.
Yes.
And overfitting.
Like not well. Like the data is not representing actually your population. That's also a major issue, I say. Yeah. You just have data available from purposive sampling. It's not a statistical sampling design then. And then your estimations might be completely off for the whole population you're actually targeting.
So what we do is also we try to look at the remedies. We try to set the candidates. We try to look at the remedies for sterility, for the extrapolation, for the remedy for overfitting, for the remedy to bias. The remedy to bias. If there's like, let's say the point samples overrepresent one part of the landscape.
There are different approaches like down-weighting the clustered ones, but there is always a difficulty on what basis do you do that? Because do you do that because they're spatially clustered, or are they clustered in feature space? Without knowing, without having like more information on your target value in your population is usually difficult.
What do you think about this? I started doing it blindly and I started getting mistakes. The idea of the of model-based statistics, where they then looking, okay, which transformation those things like in a science and model. In their case, they would nothing more less statistics. Right? But now, as I start using it, I actually realize that no, it's just a complex statistics. So actually, you have to get better statistics if you don't understand it. It's a paradox of it. It appears, it's a illusion that it's easier to use it, but you have to go back and think about the bias, extrapolation, the overfitting, and you have to understand the more complex mathematical models. You agree with that?
I clearly agree. Because I mean, in this field, there are also people like entering from computational science, and they just have a look, or they just, in their view, it's just the algorithm, and they keep, they lose track of all these concepts behind that are actually statistical and need to be treated.
Coming from the XH, if you don't see what you want to see, just troubles, no more data, and when it comes out, that's really the one key that is interesting. Understanding mathematics behind it. It's just much more complex. So.
Yeah, and the point is just having more data doesn't mean your end product will be any better.
Yes. Okay.
Because if the data is crap like the other data you already have, well.
I'm sorry for interrupting, but
No problem. Any other comments?
We can define.
For the online listeners, the question was, how can we define the area where we actually extrapolate within the feature space? I think this was discussed by Hannah, and there is still, it's all about like, how do we define what's extrapolation and where do we put the threshold? And there, I'm not too sure how this can actually be done, like in a sound way so far.
Well, the comments so much. Measuring your package. I have a Lasso set, and you want to know where is the relation to that. Not like it's a bit curious.
But just to remember, all these questions, they relate that your study has not been designed well. Because in an optimal world, you start with a proper statistical, or you start by definition of your population, then you add a proper statistical sampling design that can represent your population. And then you don't have an extrapolation problem anymore. It's just like fixing at the very end something that should have been considered at the beginning.
Yes, but
and
you're not
yeah. A lot of people here are usually in the situation, myself as well, that you just have data from somewhere. I have a lot of data from the archive, and this has been sampled. I have no influence on that. But still, the data sampling was expensive. I cannot just reject it. It will not be accepted by the people that actually took it in the first place. The comment was that random forest is like averaging out on the further away, or like on the extreme values in general, yes, this is to be expected because of this behavior that you can always just predict the mean in your leaf. And this means also if your values are not, or if your model fit is very, very poor, random forest did not find good relationships, then your leaf is scattered with a lot of different data, and then this means you have a certain tendency to your population mean or to your data mean. If the random forest model fit is poor, you have a tendency that your prediction will be the mean in the end of your data. The question was if this minimized squared error, or there is an assumption behind, and if this has been like elaborated somehow. Yes, I mean, it's if you operate with a minimizing the squared error, you're basically in a classical ordinary least squares framework. I've seen some publications that have tested it and have introduced there as a criteria a robust error loss, and it's instead of like a squared error, an absolute error. And I think they also used some Hooper error loss as further criteria, and at least on their data set, this was an advantage. But it's still, I mean, the whole tree as such does not make any error assumptions, but the single splits, they optimize on a squared error, yes. Or the overall accuracy, the wrong classifier. The question was the influence of dispersed data, and from my experience, I had data that was really positively skewed. I fitted also log transformation on those. The result was very similar. But I mean, this was just for my data set. I would not generalize it as a general rule. But still, it seems because you always have a binary split, you do not do a linear fit that can be extremely distorted with outliers. And this binary splitting might still be having a certain robustness, even though it's a squared error loss. But it's clearly, I'd say it would be good if like random forest implementations would allow to choose the error loss there. I've not checked if this is possible now already. It's a new discussion, I think. Yeah. Any further questions? So I briefly explain the boosting algorithm, which is a stepwise forward machine learning procedure. Basically, you start with a model, and with a linear model, you basically start with adding an intercept, and this gives you the mean, and then you compute the residuals. Then you fit a next model. In this context, they talk about base learners. You fit a next model to your residuals. You update your parameters as usually as the sum of these models. And is this update not as in a normal stepwise forward procedure? You use like an all-in approach, but you apply it's exactly the same thought behind it as with the Lasso. You apply a shrinkage. This means you have here a parameter that makes the model you add being only just a small step. And this means this is like the model is growing very slowly, and this means it's a weak learner. And then you iterate over that, and you keep adding covariates, and you keep adding like model snippets, so to say, in a stepwise forward fashion. And what you have to find is basically how often you should do and when you should stop. And these base learners, they can even be just normal linear models, but they can be splines, they can even be single trees. And this is then like the boosted regression trees. And basically, if we are like in a splines or in a linear model framework, this gives me a selection tool, or basically a selection algorithm for a high-dimensional regression. So I have here a mini example. For example, this pH values here, and I take the mean as a starting point. I compute the residuals to this mean. Then I check with my covariates, and I fit linear or nonlinear relationships to this, all to these covariates. Then I select this one that has the best fitting in this step. And instead of adding it to the model equation by 100%, as we would do in a normal stepwise forward procedure, we just added this effect by 10%. And then we again compute the residuals. We add the next effect, and this means now we had temperature. And since it was only added by 10%, and maybe temperature is important in my model, I can add it again and again until it sums up to, or it is taken as often as it's the best fitting to the residuals. If it's important, it's taken many times. And then basically I continue the procedure. And here this was an example of modeling the breeding spots of red kite from publication, and there they used like linear elements, non-linear elements, and as well a smooth spatial surface. This means this is now like the first model I show here that can include the spatial location as such in the model itself. Skip that. Not exactly, because the Lasso is actually shrinking directly, or is calculating the Lasso itself is based on this formula, and it's optimizing then the formula, and this is based on a stepwise algorithm. But I'm not too sure if there is actually a relationship mathematically seen. Some methods relate where one never thinks so. And this is from this publication of the red kite, where they included for their study area then a spatially varying trend over the whole study area. So the advantage of that is finding a method that can actually include the coordinates in a systematic way by adding spatially varying coefficients over the study area. And it selects covariates because in this forward selection, not all of the covariates are actually considered. But from my point, or from my experience, it's not strongly selecting. And if we use a linear boosting or also this splines boosting, it's quite easy for interpretation if the model is not too complex. But the disadvantages are clearly, it's not so fast, and especially if you do like this non-linear spline fitting, it's quite difficult for the setup. And I had the experience that I had, like, for example, geological units, and if I have like 12 geological units, and my splines have just the degrees of freedoms of my splines is just 5, so they're under So there is a penalty that these geological units are not well selected. So for certain categorical covariates, they have a disadvantage, especially if they are important. And interactions, the interpretation is, I mean, as I said, it's possible, but if there is no strong covariate selection and we have many, it's the same as other models, it's a bit difficult. And if you work with not with tree-based, but with splines and linear based learners, then you remain in a linear framework and you have assumptions about your errors. The Gaussian assumption about your errors remains, you still have to do transformations and so on. And the prediction uncertainty, again, is just with a bootstrap approach. So now, there are even publications that they compare both, but usually they are quite similar. Should I use now boosted trees or should I use random forest? I mean, the boosted trees, they have a bit, the select covariates weakly. Random forest doesn't, just uses everything. We have covariate importance for both of these methods. Tree-based methods usually yield that. We have predictive accuracy is from the studies and also from my own data. It's usually the boosted trees were a bit lower in performance, although never completely off. And for random forest, usually, at least is in my data sets and also with some other publications, although not all of them compared all the methods I show here, random forest was usually performing very well, or at least slightly better than the others. Prediction uncertainty with boosted trees, we don't get that directly. We have to do a bootstrapping, a simulation. With random forest, we have that. And this procedure, since it's a forward stepwise approach and it fits on the residues, it's expected to reduce the bias in your final prediction because it can slightly adapt and correct for the bias. The random forest always fits directly on your original data distribution. About the speed in fitting, I don't know. I'd say it's roughly the same. So, any questions so far on these tree-based methods and the boosting? I don't fully understand. What do you mean with measurement uncertainty? The uncertainty of your lab measurements, for example? Positional error. Okay, the question was how can we consider like the measurement error in the original data? And I'm not aware of any of these methods that they have like a procedure that handles that directly, but what's always possible is do an error propagation scheme. And this means basically in the resampling of the random forest, you could consider like these different variations in your of your actual response. Yeah, exactly. At the beginning, at the model input, and then this means this would then be considered in your model prediction and also in the uncertainty of your throughout the process. But this is only possible for the bootstrap, or like a random forest that already does a bootstrapping. I think Andreas has a comment on that.
I guess the principle, the weights, with the few data sets, and you can read different stuff. But it was funny what sense of the it's a lot of vehicle
I don't remember the arguments, but seen from the algorithm that has to be. But I have a question back. You said you would use the weights like the inverse of the error. Is this a good? Okay, okay.
I have one question about local versus global. And we have a lot of discussion. When you have a tree-based, models. And if you include, for example, you have different countries, let's say, do you need to do local models at all? Do you need to do per country? Because to me, it's embedded, certification, it's embedded in the modeling.
This is a very difficult question, I'd say. And if local models, then not by country, but by units that are defined by your response. And this might be countries if the data sources are different per country. But maybe this might be geographical regions. But there, yeah.
Or you could do, you don't take the country as covariate, and you see local models. I think the thing is maybe to do some other models, but anything
if you use local models, you introduce follow-up problems, because then you have like your prediction maps usually have then a gap towards the next region that you have then to post-process. So I have a tendency to go for global models, but introducing like the covariate that would build up the local model. Or there would need to be really a strong reason why to build local models. I would prefer to have a model that can actually find the relationships in this local area. Yeah. So we just For the end, we come to the model averaging, and this is basically combining different methods as not just like as with random forest, as there are combined different trees. Here, you would just combine any method. It means you calculate the lasso, you calculate the support vector machine, and you combine these predictions for your final prediction. And the idea behind it is that every of these methods can capture a certain relationship in your data that the other methods cannot. And if you combine in the end the predictions, you have like all these different relationships that have been captured by the different methods, you can combine into your final predictions. And moreover, you also some sort of balance disadvantages of one method, especially if you have like an extrapolation procedure as Lasso, and you have a procedure like random forest that is not extrapolating, which I'd say both are wrong, then the model averaging gives you something in between. And therefore, it's, if you see in the literature for applications of model averaging, this is usually sometimes slightly and sometimes clearly outperforming just one single model. And if we have a look just for linear models, if we combine different linear models, there is actually mathematical proof that combining several different linear models, they outperform always the single model. For these complex machine learning methods, such a proof is missing, but we have to test it on our data. And there are, of course, different strategies how you can do that. One would just be take a simple plain mean. One would be take a weighted mean and use, for example, the mean squared error or your R square to penalize a bit the methods that did not perform well. And there are also other approaches. There is even an R package, I think it's called Granger, that does pixel by pixel combination. And it's considering the uncertainties at every pixel. And this means like the weights how to combine your methods are recalculated at every pixel. And it means if you have an area where the Lasso is very good and random forest is very poor, then the predictions of the Lasso are upweighted and the ones of random forest downweighted for just this area. And in another area, it might be the opposite. And there are approaches that you can even, you have like 5 predictions, you fit a new linear model to your response again. But here, please, if you have like a proper test set to evaluate your error in the end, don't do the fitting on your test set. Otherwise, you have no independent test set anymore to evaluate your error. And there are also Bayesian approaches, but I have not used them so far. It's called the stacking stack generalization. So it remains one last problem that I've mentioned quite frequently. We have a lot of machine learning methods, but they are not explicitly spatial. And with most of them, we have the problem that they do not consider our spatially correlated data. So one way out would be, but it seems to me also a bit, all way outs are a bit suboptimal, or maybe someone has a better proposition here. One would be to use this regression kriging. You fit any kind of model, then you test if you still have residual spatial structure, and you fit another variogram onto your data, and you do a kriging step as a last step of your modeling. But this, of course, it takes 2 independent model fits, and your prediction intervals in the end will need a simulation to have the full prediction interval. Another a bit ad hoc method I usually go for, I add the x and y coordinates as covariates. And since if you just add x and y, this can start to, especially for tree-based methods, the trees start to do partition on these just x and y coordinates, and you get a chessboard in the end. You have like, and then you have these very strange artifacts in your predictions in the end. So a way out would be not just to add x and y, but just also to rotate them with a transformation coordinate. So at least it's splitting in the trees is, can be done into different directions. And the third way is basically to add this smooth surface, as I showed with the boosting, with the additive model. But there, from my experience, either it's not smooth enough because I do not allow for many degrees of freedom, and then it's actually not improving the model at all, or if we allow a lot of degrees of freedom, then it starts to over-adapt and we have an overfitting problem. So all of these three approaches I find a bit suboptimal. I would need to do a further literature screening if there is not a better solution right now. Maybe someone has a comment on that. Yeah. Yeah, that would actually be like the. Aha, but this means this is this approach already implemented in one package, like the first. Okay. Yeah. Okay. Say again? That would be this approach here. Or not? Yeah, like rotating the coordinates. Yeah, just did it by hand. Yeah, that's what I use at the moment. Yeah. It works, okay. It's yes. Yeah, but it's a bit ad hoc as well. So, as and then you have the those in the edge, you reach to the edge of the area. I think he mainly used like elevation differences and so on. This is common. Ah, this is an okay. Yeah. But you would then calculate the relative distances to every data point, to the edge of your study area. Mm-hmm. Yeah, exactly. Aha, like grouping it. Yeah, okay. So I'm coming to the end, and I hope you have a bit more idea of all these words here. And now is the question, is this a sensible thing to do or not? Any guessing? So you propose still to compute these 80 models, but using weights for the model averaging. Any other?
fine tuning and other ones that really go whereas.
There was someone at the back. Can you speak more, please? Yeah. I mean, basically, as Anatol said, and just beforehand, it's if you have like these 80 models, it's very likely that many of these methods are extremely similar. And the results or the structure you find in your data, they just find roughly about the same structure. And so a better approach would be to take a step back and think first and check, okay, I take one of this family, I take one of this family, I take one of this family, and then combine them, and maybe then you have 5 or maybe maximum 10, but most likely the 78 will either not improve or overfit your data. And result in likely a lot of work, unless, and will most likely also result in you not understanding every single method and correctly apply it. So therefore, better use methods that you are familiar with and apply them soundly and be sure what you actually do, instead of just like having an all-in approach. I'd go for that. So I brought some exercises, but they are mostly self-explaining. So we will not be able to go through all of them. The data is from a study area nearby Bern, where we had roughly 1,000 sites sampled for different soil properties. And I've already split them, since these are data from the archive. It's not a statistical design. So I already split them with a meaningful, with like expert knowledge behind into a validation and calibration data set. And there is many covariates, so you can actually also work. I don't remember how many there are, 150 or so. So you really have like a data set with many covariates that you can start to work with it and test it. The exercises are on GitHub under this address. It's also in the Google Calendar. And John Lewis, that showed a presentation on Monday on tidy models. He did a translation of my codes for parts of these models. So people that work in the tidyverse environment, they can have a look on this code as well. my code is partly rather conservative, using like normal R base procedures. So the exercises consist out of a Lasso example, support vector machines, random forest, and then different gradient boosting. I will directly jump now to the support vector machines, because I assume the Lasso is maybe, it's quite a specific method, maybe not the first you will be using. So at the beginning of your of the data, I'm sorry, I have a bit of problem with scrolling around. Touchpad also doesn't. And, so. Basically here, this is a list of all the packages you're going to use. I use here, as already also shown by Hannah, the caret package. I don't use it for everything. For the random forest, I usually use Ranger directly. And then you also need the kernlab, that's to fit the support vector machine. And of course, I also have used the package parallel for parallel processing of some tuning. In this code chunk, I basically select the data. For most of the examples, I just selected the data that has no missing values in the response. For the calibration and the validation set, but just for this pH response. And according to the data description of this Bern data set, you find the covariates starting from the column 13. Then for a support vector machine, you maybe are not familiar with this function model matrix. You have to set up a model frame as for a linear model. Usually like the function lm does that in the background. So what it does is basically setting up your dummy covariates, because I have covariates that are categorical, and it turns every category from for example, my geological units, it turns into 1 and 0 just for every level of this category. And here I remove the intercept, because this is not needed in a support vector machine. Then I set up a train control. This is this control function from the caret, and I use a cross-validation, a 10-fold cross-validation, and it should also save the predictions, just the final ones. And the support vector machine tuning is done in 2 steps. As you maybe remember, we have this C and this sigma tuning parameters. And in a first step, you basically search for the roughly whereabouts of this tuning parameters. And in a second step, you do a proper tuning to find the exact location of this, or like the exact location of this tuning parameters. So we have here a first training step. Again, the function of caret. Then we use radial basis functions for the support vector machines. So we use non-linear support vector machines. And we also do a scaling and the centering of the data. And in a first step, what do you mean with and without refitting?
So if you do a 10 fold, then you have to refit more than 10 times.
Yeah.
Or you can do 10 fold and then 10 times check.
From my point of view, cross-validation has always to be done with complete refitting. Okay. Otherwise, it's not valid. Okay. And then you get out, like from the first step, you get this sigma. And then here, I basically build up a vector that has like values just before this sigma and just after this sigma. And those are then tested in a second step. And with the caret package, you hand over a tuning grid that has basically for, like, if you have like two tuning parameters, it's basically a grid which combinations you want to be checked. And all these combinations that you have in this tuning matrix of these tuning parameters is then being tested in this second training. That is done here with this tuning grid. And just as a warning, it takes a while to do this tuning, depending on the capacity of your machine. Then it gives me cross-validation, the observed and predicted cross-validation predictions, and here this is calculated on the validation set. And I usually, for this type of scatter plots, I add a smoothing line. And if this loss scatter plot smoother lies roughly on the 1-to-1 line, I can directly see there is no bias involved. So for the cross-validation and also for this external validation, we can assume no bias, but of course we have a certain variation around it, so quite a variance. I think I've not calculated here the R-square, but this could be easily calculated from these predictions and observations, of course. And here is how I compute the predictions. And again, of course, for the predictions, my data frame has to look exactly the same as for the model fitting. So I again use the model matrix function to produce my new data. And that's how the support vector machine is quickly applied. So it should be easy to implement for the competition, I think. Any questions? Here, this is just the application of random forest. This is very simple and straightforward if we do not do any tuning. I just use this function ranger. There is also a package called random forest. There are several packages actually doing quite the same. They have different arguments, a bit of a different speed. Ranger is, I think, has a lot of arguments in addition, and it's fast, so it's a good package. And again, I mean, you just give the X and the response the Y, and it uses like default tuning parameters and gives you a first model fit. Now I just implemented by hand that you can see you do not always need to use the package caret. You can, it's also quite easily done to do tuning yourself, especially if there is something you're not sure if caret actually does it the correct way or the model is missing from the caret package. I basically set up a function, and this function is then applied below. And this function takes the mtry, takes the calibration data and the list of covariates. Then I have to set the seed to initiate the random number generator, so the random numbers always start at the same point. And why is that? Because remember, we have like two random components in random forest. One is the resampling, and one is this mtry, the covariates that are taken at random for each split. So then we basically fit a ranger model with this mtry that we specify here, and the function returns the model error for this specific mtry. Here we set up a sequence for the mtry, and since we don't want to wait too long, we just take every fifth value. We reduce this sequence. And here, this is application with MCLApply. This is parallel computing directly, but I'm afraid I've not tested it since I could not be bothered, to be honest. It might not work on Windows. But most likely there are people around with the snow and do parallel. Yeah, exactly. Just for Windows, if you use one core, it works, but it does not do any parallel computing. Okay. But it's a pity it does not I think the package do parallel, where you do need to open clusters and then close them again, would then also work on Windows. But I'm not the right person to ask. And here basically with this apply function, this mtapply works exactly like an sapply or an lapply. You hand over your sequence, and this is the function that I just defined above. Here you choose the number of cores of your machine, and then you also specify if the seed should be reset or not for each fold. This depends on what you do in your function. And then these are basically the arguments that you hand over to your function. They have been defined just here above. These are basically the arguments that are handed over. And then it does, this returns just a list of all these errors. And I put them into a data frame and search for the mtry with the minimal error. And of course now, since I know the optimal mtry, I can then fit a random forest model with this optimal mtry. I have here a validation plot where you can see usually the mtry is, or at least in my applications, is some sort of flattening up. It's if it's very small, the model error is usually quite high, but then it's lowering at somewhere there is an optimum. So that's just a random forest with manual tuning without the caret package. Any questions? But to be honest, for the random forest, if you just use the default values, because usually the fits are also not too bad. I mean, you can apply a lot of computing, and in the end, your R² is maybe very, very little. It's getting better. But it depends on the data set. It can improve quite a lot, or it can improve just not much. And this would be the boosting with trees as base learners. Here, the setup is basically roughly the same as for the support vector machines, because here I again used the package caret, where I set up a tuning grid. And for these boosted trees, the main tuning parameters are the number of trees. This means the number of stepwise forward iterations that it's supposed to calculate, and the interaction depth. This means how many splits should a tree make. And with these boosted trees, usually you do not grow a full tree. Like in random forest, you basically grow until you have just like these five data points left over. For the boosted trees, usually there are even like, this is a tuning parameter. You check if you do 2 splits, if you do 5 splits, 10, or you check what's the best option here. Then usually the shrinkage. This is the if like a tree is added with 10% or with 50%. This is not sensitive, but it needs to be small. And here is the minimum number of, if the tree is growing big, the minimum number of in each, that's basically the node size argument in random forest. Here I just set it to 10. I don't think it's very sensitive. I once played around a bit, but didn't play well. Then it uses this train control here with exactly the same arguments as above. Cross-validation, tenfold, and save the predictions. And I told it to shut up. And I hand over the tune grid, and the package I use here for the boosted trees is this GBM. The rest is the model specification as above. Then this gives me the best tuning results. I have like 77 iterations, 77 trees. Interaction depth is just like 2 splits. And the rest I did not tune, I kept fixed. And with that, I computed a prediction on the Bern grid. This is the actual raster data. This results then in a little bit of salt and pepper pattern, because it's zoomed in a lot. And we have certain covariates that have quite a noisy variation within it. The blank areas are basically streets and houses. So this is they are missing data in our prediction. So now we still have like boosting with linear base learners and the Lasso. I leave that to check out for yourself. Any questions on the applications? The question was, what's the good number of samples to acceptable numbers of samples to start with machine learning? I'd say it depends on what you want to achieve. For me, if you have 100 samples and you use a machine learning, it's explanatory analysis. You will not be, from my point, or your study area is very small. just work on field scale, for example. But if you have a large study area, 100 samples, and you apply machine learning, most likely your model will, your 100 samples will not be able to cover all the relationships in your study area, and so most likely your predictions will be off. It has to, from my point of view, has to be evaluated always in perspective of what you try to do. So, if there are no further questions, I'd say we go to lunch.